Thank you for the invitation. As you can see, the title of the talk is Inverse Coefficient Problems for the Space Fractional Heat Equation. This is a joint work with Professor Durub Khan Suragan from Nazarbayev University, Kazakhstan. And in this talk, we consider the problem 1. This is a heat equation with a fractional Laplacian operator and S changes between 0 and 1. And we consider this equation with this type of initial condition and this type of boundary condition. Because of this fractional Laplacian operator, we have to formulate boundary condition in this form, not only the boundary of the domain, but also the outside of the domain. The value of the function should be 0. And our aim is to recover coefficient P of t of this problem using the following types of our determination conditions, the conditions 2 and 3. I will explain in detail later. Now, before formulating our problem, I need to recall some properties of fractional Sobolev spaces, some properties of fractional Laplacian spectral problem, and so on. So this is a motivation part of our work. Our equation includes this type of fractional Laplacian operator. This operator will be a generator of a symmetric stable Levy processes. It is connected with maybe probability theory. So we need some fractional Sobolev spaces to work with our problem. This is the norm of the H S omega, the space. The norm of this space is defined by formula 4. And with the help of these Sobolev spaces, we can introduce H0S omega as follows using formula 5. And then also the norm 6 is equivalent to the norm defined by the formula 4. And we have the following fact for these spaces. If we introduce scalar product in the following form, then this space will be Hilbert space. Okay. And we have fractional Laplacian operator on a bounded domain of Rn. It is defined by formula 8. And here, this is a constant is defined by this equality. And so we are considering on a bounded domain, we put here omega to denote this. And we use the following Dirichlet Laplacian spectral problem and its properties. This is a eigenvalue problem. The weak formulation of 9 can be represented by formula 10. And we have the fact that the spectral problem has countable set of eigenvalues, and moreover, the eigenfunctions corresponding to these eigenvalues forms an orthonormal system in L2 and orthogonal system in the Sobolev spaces H0S. Additionally, we have the following type asymptotic formula for sufficiently large values of K. We use this asymptotic relation while we are studying inverse problem. And also one can show that this fractional Laplacian operator is self-adjoint, so the equality certain is valid. And also, I think I skip this presentation. This is a definition of some Banach spaces. And now we move the formulation of our first problem. We consider the equation 16 in a bounded domain of Rn and with the following Cauchy-Dirichlet conditions. And we assume that phi and f are given functions from they satisfy these conditions. Fourth, assuming p of t, coefficient p of t of the equation is a continuous function, we introduce the definition of the weak solution of our problem 16, 17, 18. We call a function u is a weak solution of the problem if it belongs to these type of spaces, and also it satisfies equality 19 for all the functions from the space H0S, and also U should satisfy the initial condition 17. This is our inverse problem 1. We should show the uniqueness and existence of a pair of functions U and P such that P should be continuous and U should be a weak solution to the problem, and they satisfy the following type over determination condition. Here Q is a fixed point of the domain omega. Now we will go to the study of the inverse problem. We will seek a weak solution to the problem in this form. Here phi k of x is a eigenfunctions of the fractional Dirichlet Laplacian spectral problem, and using these relations from our equation, we will have this type of ordinary differential equation. And with the following type initial condition, and it is easy to see that the solution of this Cauchy problem has the following form, formula 24, and substituting this expression of ukt into our into 21, we get the following representation, formal representation for the solution of our equation. But we assume here p of t is a noun function. And if p of t is a noun function, this is the solution of our problem. Next, we proved that under these conditions, this solution will be a weak solution to the problem for any p of t, any continuous p of t. So phi and f satisfy these conditions, then uxt defined by 25 will be unique weak solution to the problem. Detailed proof of this is given our published work. This work was published in Fractional Calculus and Applied Analysis. So now I will move the studying of the inverse problem. We introduced the following set of functions. dm omega denotes the set of functions satisfies the following properties for some natural number n, and we assume that m should satisfy this n inequality. Then we have the following fact: if phi from this set of functions, then we have this type of inequality. This gives us the convergence of this series from the left-hand side of this inequality. Here, lambda is a series using the Weyler's asymptotic formula. One can see that this series is convergent. So, using this, we can conclude that the series, the left-hand side of this inequality, also converges. This is some part of our result. We choose a point Q in the our determination condition such that more precisely all of the eigenfunctions should be bounded. This is our assumptions, and this is our main result for the inverse problem 1. Assume that the assumptions I and 3I are satisfied, and also the conditions of lemmas 1 and 2 hold, then the problem 1 has a unique pair of solutions U and P. Now we will show the proof of our theorem. We introduce this type of new unknown function, and by multiplying the both sides of 25, we get the following equality. And here, using the our determination condition, we get the following in equality. And as we assumed W of t is non-zero from the last, we have the following equalities 26. If we can show the convergence of this series, then we can consider this as a second kind Volterra integral equation with respect to unknown function r of t. So to prove the convergence of this series, we applied our lemma under these conditions. This type of we get this type of series. So under the conditions of lemma, this series convergence. Okay, now this is a proof of convergence of the series. We can write using the self-adjoint property of fractional Laplacian operator. We can write Fourier coefficient phi k in this form, and here, and assuming at the point q eigenfunctions are bounded, the Majorant series for this functional series will be this one. And using this representation and applying Cauchy-Schwarz and inequality, we will have this inequality. And here, by applying Bessel's inequality, we obtain this inequality. From the last, we can conclude that this series is convergent because using the Weyl asymptotic formula, this series is convergent, and we assumed that phi is from the set of functions dm omega, so this is finite. So we proved that this series convergent, and similarly one can prove the series with respect to f also convergent. So now we move how to find an unknown function p of t. By differentiating this equality, we can find p of t in this form. And we have some assumptions, so we decided to provide some examples which satisfy all of the assumptions of our main theorem. So for this aim, we consider the following one-dimensional spectral problem, and here s between 0 and 1/2. And from the paper of these authors, it is known that this spectral problem has a countable set of eigenvalues, and also corresponding eigenfunctions forms a complete orthonormal system in L2. Additionally, in the paper of these researchers, it was proved that all of the eigenfunctions of the spectral problem are bounded. So using this result, we provided the following form example. If we consider one-dimensional, the following inverse problem, and if we take as an initial function the first eigenfunction of the previous spectral problem, and if we take this type of our determination condition, then this example satisfies all the assumptions of our theorem. This is a proof, and to find to define coefficient of the inverse problem. In this case, we have the following type of integral equation, and using this, by finding this integral, by solving this integral equation, we will have the following form of unknown function, and using this, taking derivative of this function, we can recover a known coefficient p of t of our problem in the following form. Then the pair of u and p will be unique solution of our inverse problem in example 1. Now we move to our second problem. We consider the equation in the form of 29. Here also minus delta s is a restricted fractional Laplacian operator. Similarly, for any, our aim is to recover a known time-dependent coefficient of the equation R of t. First, assuming R of t is a continuous function, we introduced a weak solution to the problem 29 with the initial and Dirichlet conditions as follows. Definition 2, a function u, which is from the class of functions, will be a weak solution of our problem if it satisfies the following identity for all the functions v from the space of functions, and also it satisfies the initial condition 17. This is a formulation of our second problem. Shows the existence and uniqueness of a pair of functions u and r, such that r should be continuous and u will be a weak solution to the problem, and u should satisfy the following form of our determination condition. And in this case, similarly, we will have the following form of initial condition for the Fourier coefficients of the unknown function, and solving this initial problem, we will have the following representation for the ukt, and substituting this representation into 21, we get the following formal form of our solution of our problem. And first we proved that on the assumption if r of t is a continuous function, then the function defined by equality 33 will be weak solution of our problem if phi and f satisfies the following conditions. Then this is our result for the second inverse problem. If phi belongs to the set of functions and f satisfies the following conditions. Moreover, if the w and w satisfies the following conditions, then the problem 2 has a unique pair of solutions u and r. And I should say that the detailed proof of our result is you can find this source. This is our recent published work in fractional calculus and applied analysis. That's all. Thank you for your attention.